As you get those phones away, let me tell you what we're going to be doing today. A couple of things kind of as we look forward. So today we're going to look at lesson 6 here shortly. We'll be starting with some review. It's been a while. And so we're going to kind of review the first half of Unit 5 and then get into Unit 6. Keep in mind that the end of this semester comes really fast from here, right? We have this week. Today, Thursday, we will be doing STAR testing and lesson 7. I know everyone is so excited, but at least I didn't do STAR testing today for you. Next week, we finish up Monday, Wednesday for your class, the last couple of lessons in this unit, and then we're done. And then we review and exam week. Exam week for us is our Unit 5 lesson, so it's our Unit 5 assessment. It's not cumulative, it's Unit 5. And so if you can kind of stay on top of what we're going to review today and these next couple of lessons, you'll be in good shape for that. We're going to start with a little bit of review. So what I want you to think about is some of those big words, those big ideas that we talked about before. You might have your notes out from before break. That might help you to remember some of it. You should have. There were 3 classes that we did in Unit 5 before. Let's just take a look first at some of these big words, and then I'm going to kind of lead you through some review. So the first one, degree. Does anyone remember what degree means, where we find it, what it tells us? What can you tell me about degree? Ellie, what do you remember? You're partway there. It has to do with the exponent. What about the exponent? Or which exponent, I should say? More specific. The biggest one, right? The biggest exponent tells us our degree. What does our degree look like in our graph? Of which packet? All of the ones are in Canvas. If you want me to print them out, you can either email me or see me during EB. I don't have them right now on me, but they also are all in Canvas. What does the degree look like in a graph? Ellie, do you remember what it tells us or what it shows us?
I think it's how many up and down.
Yeah, kind of like those pieces, right? Not necessarily how many curves it has, but how many pieces it has. What about a constant? What is a constant? What does it tell us? Where do we find it? What do you remember about a constant? Constant. What is the constant? Where do we find it, either in our equations or in our graphs? What does it look like?
If it's 2x2 plus 7, it's 7.
Yeah, that number that has no variable on it, right? That's just the number by itself is our constant. Where do we see this in our graph? Remember what our constant tells us in our graph? The y-intercept, right? So we can see it on the graph also. What about the leading coefficient? What is the leading coefficient? Where do we find it? We actually don't know what it tells us specifically yet. We'll get into that, but what is the leading coefficient? What does that mean? Leading coefficient. What does it mean? I would say you're halfway there, but remember that the one in front could change, right? We could rearrange those terms. 3 plus 2 is the same as 2 plus 3. We could have moved them around. How do we know which one is leading? Sometimes you're the first one when? Almost. You're really close to it. In standard, the first one in the equation when it's in standard form, right? And it's always connected to that biggest exponent, right? Wherever you found the degree is always the one that had the leading coefficient, right? They go together. What about standard form? You already kind of mentioned standard form. What does it look like? How do we know if it's in standard form? What has to be true about it if it's in standard form? What should I not see any of if it's written in standard form? Parentheses, right? If standard form has, it's all kind of multiplied out. It also in standard form we looked at is always written from the biggest exponent down to the smallest, down to the constant, right? They go in a certain order. Relative minimum or maximum. We looked at on our graph, if there's a lot of curves, we might find a relative minimum or a relative maximum. Where are those? What do they look like? Do you remember? What's in your notes? Ellie, was that a half hand up?
I think it's something like the highest point that it reaches.
Yeah, so when it curves, right, and kind of has that upper point, a relative maximum, it's the highest in comparison to what's around it, right? And then it might have some of these curves that go down, a relative minimum. In relation to what's around it, it's the lowest. It might not be the lowest of the entire graph, but it's the lowest in relation. And then finally, the last one before I give you some review to work on is the idea of evaluate. If I give you a problem, I give you an equation, and I say evaluate when x equals 2. What does that mean? What is that asking you to do? Evaluate. Yeah, plug it in, right? We're kind of doing the math. Plug that value in, find what it equals to. So what I want you to do, in a moment, I'm going to pass out our notes for today. You will find that the very first paper here is kind of, it's titled A Look Back. It has a bunch of review problems. These are actually taken off of previous homework problems that we didn't do, that I didn't assign to you. Going over a lot of these big concepts, a lot of the ones that we just kind of talked through, but I want you to have some time to really look at, review through these. It's really important in your group that you work on this page, this paper, front and back, review with your group. Some of you may remember things from a lesson about finding the minimum and the maximum. Maybe you're really good at looking at the graph and picturing things. As someone else in your group was maybe here a day when you weren't here, and they remember very clearly about the degree and the coefficients, right? When you put all your brains together, you have a lot of knowledge, a lot of information in there that you guys can work on to kind of work through some of this review. If you were here for all the other 3 days of this unit, this should be a really good refresher for you. Kind of bring all those topics back, especially here when we're in the midpoint of this chapter. If you missed some days, this is a really good chance to see the types of problems we were working on, to ask some questions in your group. So what I want you to do is I'm going to give you about 15 minutes. So we'll go until about 11:40. And I want you to do as many of these as you can. Use your notes, work in your group, really use it as a time to review and to refresh. Please only do the first paper. The next two are going into our notes for today. Just do this first paper with the review on it. Okay, I want to make sure that before we take a break for lunch that we have some time to look at a few of these kind of review topics. Now, the first part is vocabulary. And if you didn't get this filled out, I would really encourage you to kind of keep working on it. And don't just simply go to Google and write down their definition, because that doesn't necessarily mean anything to you. Think about how do these words appear in the practice we've been doing? How do they appear in the notes we've been going through? How could you write these in your words? Maybe draw yourself a picture, give yourself an example of them so that you can be thinking about the vocabulary. But I want us to get to, if I can get down my page, there we go, to some of these practice. I want us to take a look specifically at some of them. So the first one we're going to look at is this one that's asking about the degree, the leading coefficient, the constant of each of these. Okay, so let's start with this one. Who can tell me in letter A, what is my degree? What is the degree for this one? Ezzy, what is it? 5, right? Our degree is always that largest exponent. You might mark it, make sure you somehow put a word in there so that you know what we're circling. Which one is the degree? Which is the leading coefficient? Give yourself some good notes so that this can really help you as we kind of sum up the first half. What's the leading coefficient? Almost. I would say that 2x5 is our leading term, but which one is our leading coefficient?
Wait, is leading coefficient the biggest number in front of x?
Say again what you said. Nope, it has to be the leading one. So you're right that 2x to the 5th is the leading term, but which part is the coefficient? Mimi? Just the 2. The coefficient is just the number out in front. So this here is our leading coefficient, right? Yeah. Yeah, because it's written in standard form, right? So the degree is the highest. It's leading. It's out in front in standard form, but our coefficient is just the number. What is our constant in this part A? What's our constant? -6. Yep. Okay, part B. What's our degree in letter B? What is our degree? The biggest exponent? 3. Our leading coefficient? Yeah, there's nothing written here, but it's a 1 out in front, right? What's our constant? 2. Again, if I were you, I wouldn't just mark them like I am here on the paper. Write yourself some notes. Which one is the degree? What's the leading coefficient? So you can look back at it. Now, part C, be really careful. There's kind of a little bit of a trick in here. What's the degree of this one? 3. Our largest exponent is 3. What's our leading coefficient? Normally, a leading coefficient is in front, right? But what's wrong with this equation? Gracie, do you see what's wrong with this equation? Yeah, it's not in that standard form, right? So either we can put it in standard form, or remember that the leading one is always with the biggest exponent. So here really is our leading coefficient. And our constant? 5.4. We know what that constant means. That constant means that it has a y-intercept there. In 2 classes, so for you that would be on Monday, we'll be looking at kind of what that degree and leading coefficient together kind of tell us, but right now we just need to know how to find it there. All right, the next problem says choose all polynomial expressions that are equivalent, that are equal to, that have the same pieces in it as that one that's given to you. Does anyone see one that's the same? C definitely is. C is like the same, right? There's another one in here that's equivalent. Gracie? E. It has all the same pieces, just it's moved around, right? Because it's addition and subtraction, we can rewrite it. E is just not in standard form, right? It doesn't go from biggest to smallest, but it has the same values. The next one said, if you're given this equation, evaluate at x equals -2. What do I need to do here? Plug it in, right? Be super careful. You'll remember if you were here the day we looked at this in class, order of operations is important. Parentheses is really important. -2 with parentheses cubed or squared is different than -2 squared, right? Those parentheses are really important. If you plug this in correctly, any guess at what it shouldn't be a guess. Any idea what the answer would be? -1. If you plug this in and got a different answer, go back and check those parentheses. Okay, in this graph, which point is a relative minimum? Gracie, which one? A is a relative minimum. Can anyone tell me all these other points on there, they're not minimums, but they're other important parts of our graph. Anyone tell me any of the other ones? What is B or C or D? Ellie, which one do you want to tell us?
B is like the y.
Yeah, B here is our y-intercept. What else do we see on this graph? C is the x-intercept.
Wait, why is A the relative minimum?
Because notice it's at the bottom of one of those dips. So in comparison to what else is around it, it's the lowest point. It's not the only one on this graph. Is there another relative minimum here? Like right here is also a relative minimum, right? It's just not labeled on there, but there can be more than one.
Wait, so if there were 2 points, like if there was another point on X or Y, would those be the relative minimum? Because they're still on the same.
You say that again? If there was another one on Y?
Yeah, like if there was another one on if there was another one on X, would C and like if A was on X, would C and A both be relative minimum? Because
This C is not a relative minimum because it's not this lowest point in comparison to what's around it.
only counts if it's a dip.
Yeah, it has to be one of those kind of dips. This would be a minimum. This would be a maximum.
Would D be the maximum?
Yeah, absolutely. This would be the relative maximum. Is there another relative maximum on this graph? Are there any more?
Yes.
Yeah, kind of like right about here. Right, there can be more than one. That's okay. It just has to always be at that kind of curve part. In comparison to what's around it, it's the highest point or it's the lowest point. Okay, this goes back to our box at the beginning of this unit. The statement kind of says, Tyler finds an expression for the volume that gives the volume of an open top box. Remember when we made those boxes, cutting out the squares, right? He graphs the volume. This is the graph that Tyler gets if he allows X to be any value from -1 to 7. What would be a more appropriate domain for him to use? Which X's are really possible? If X is measuring the square cutout and Y is measuring the volume, can he really cut out a square that is 7 inches by 7 inches? Can he really cut out a square that is 6? It's inches, right? I think. Yeah, 6 inches. Ellie, what do you think?
Is it 0, 3.5?
Yeah, I would say really it goes up to here, right? This is really our domain. Ellie, what makes you say the domain can only be between those?
Because 3.5 times 2 is 7.
Yeah, I totally agree with that. Is there anything on the graph that could help us to see that we can't do more than that? Yeah, what happens to this volume down here? The volume is negative. Can we make a box with a negative volume? I mean, technically we graphed it, right? But that doesn't mean it like applies to the situation. So I would say a more appropriate would be from 0 to 3.5. This is negative volume. We can't have this. What's the appropriate maximum volume for his box? If you had to approximate what that is, where would you find it? What do you think the biggest volume is that he could have? Where am I looking for the biggest volume? Kind of where it hits that highest point right here, right? What do you think that is? Maybe 54, 55, something like that? Again, it's approximation. So as long as you're kind of thinking about what that graph is telling us, right? We can graph things, we can draw these polynomials, but what do they really mean? Can they really apply into those applications? And the last one. I'm going to kind of leave you with this. I want to say a couple of things before lunch. If you tried this one, awesome, I can kind of take a look at it before lunch. Otherwise, this is very similar to what we're going to start in with after lunch. So I want to pause there. The one other thing I forgot to say kind of as we started, over the weekend, you should have seen that, not the weekend, it was a long weekend. Over the break, you should have seen your Angry Bird projects win in the gradebook. One note that I would remind you of, especially for those of you who worked with someone, you didn't do the project completely by yourself. Please remember that the project was out of 78 points, and 18 of those came from your quiz that you took by yourself. So you and your partner or partners may have not had the same scores because you didn't have the same quiz score, right? Your project part, the other 60 points from your math work and your Angry Birds level was the same in a partnership, but your quizzes may have been different. So just if you see those differences, that's where they came from. If you have questions about those or want to see your quiz or your kind of breakdown of Angry Bird stuff, just make sure to come and see me during an enrichment block, and I can pull those out and we can take a look at them. Otherwise, let's pause there. It's almost lunchtime, and we will keep going after lunch. Alrighty, as those phones get put back away, what I want you to do is we're going to start in, in on this lesson 6. You'll see the next page after those reviews. That next page is kind of starting lesson 6. Our goal for today's lesson, aside from that review and kind of recapping the things we've talked about so far in this unit, today what we're going to do is our goal is looking at these two different forms. What two forms do we have in polynomials? Standard and factored form. So looking at these two different forms and trying to see what other information can we know about them, and when would we use one over the other, right? You'll remember if you think back to quadratics, we had factored form, we had standard form, we had vertex form. They all told us different pieces of information. And sometimes one was more helpful than another, depending on what we were looking for. And so that's kind of what we're going to look at today. How can we find some of those key features, those key things that we've learned about so far? How can we find those in both forms? Okay, so your first kind of task, this is the same as what is on the next page that you have here. Oh, mine is all buried. That first page of your notes, on this page right here, you'll see that these same equations are listed, and you have 4 of them there. I'll wait till your conversation dies down so that we can continue. You'll see these same 4 equations are written on your notes. It looks a little bit different because we've spaced it out a little bit. But again, doing one of those, which one doesn't belong? We've done these several times in this unit, right? There's not one right answer, but every single one of these has some reason that it is different from the others. And so I'm going to give you about 5 minutes. Look at it on your own first and then talk with people around you. Why are each of these different? What makes them unique? Please notice that I gave you some vocabulary words. I would strongly encourage you to be using those vocab words. Describe precisely mathematically what you notice is different between these. If you can't do it with a vocab word, that's okay. Describe what is different. But I'm going to give you about 5 minutes by yourself and then in your group. What is different about each one of these equations? What makes it unique? Okay, let's hear some of your thoughts. What makes one of these different? Pick any of them. Which one do you want to start with? What do you notice? Ariana, what do you notice? Yeah, A is in factored form, not in standard form. It's different from all the rest in that regard. What else do you notice? What's another one that's different? What's another one that's different? Ellie, what else do you notice?
C is the only one that has like a constant of -25.
Yeah. And I would say that's one of the harder ones. A lot of the other classes had trouble finding that one, right? But that constant is, all the rest of them have a constant of -24. D has a constant of -24. B has a constant of -24. Does A have a constant of -24? How do you know?
Oh,
Yeah, if you multiplied it out, right? C is the only one that has a different constant. Awesome. What about B or D? Do you notice things that are different about B or D? Mimi, what do you notice?
For D, it has a higher degree than the others, and it also has 2 exponents.
Yeah, so it has a higher degree. It's the only one with a degree of 3, right? Technically it has 3 exponents. We just don't see one of them, right? I would also say really carefully that D also is the only one with 4 terms, right? Those 4 pieces in it, 4 terms. Which one are we missing? B. Anyone see what is different about B? Cole, what do you notice?
The leading coefficient is 2.
Yeah, this is the only one that doesn't have 1 as a leading coefficient. Awesome. So again, kind of think about how these are different. Think about using that vocabulary. I know you were working on coming up with some definitions at the beginning, but practice kind of talking about those. Now, the next one on the bottom here, this 6-2, will you just either cross it out or know that we skipped it? I want to skip over that one for today. What we're going to go into next is important, and I really want to give you some time near the end to at least open your homework, maybe start on a couple of problems of it. So we're going to skip over 6.2. When you get to 6.3, what we're looking at here in your first task is we're going to take a look at how can we review how to multiply these out. How do we change from factored form to standard form, right? Not that this is something new. You've done this before. You've distributed these things. Whether you distribute each piece or you use that box method will be totally up to you. But I want us to take a look at these. I'm going to just pull up my notes here for a second. So, for example, what your task is in 6.3 is to say, how can I prove or verify that this in factored form is equal to this in standard form? In that warm-up, I heard some of you starting to think about it in that A in factored form. How would you multiply it out, right? Some of you may multiply, remember that we multiply kind of each part. Some of you might want to set up the box, that area model box method. Totally up to you. But can we prove that these two things are equal? So let's do this first one together. For example, if I use the box method, I know many of you like this one. So I'll have x plus 2 and x plus 4. Remember that when I multiply using the box method, I'm multiplying whatever is in this location on top by whatever is on that side of the box. So we'll have x squared, 2x, 4x, and 8. Now, how do I take those numbers out of the box method? Anyone remember? What is my equation going to be written as? I have 1x squared plus 2x plus 4x plus 8. Is this my final equation? What do I need to do to it? Kind of combine those like terms, right? Put them together. So at the end, my equation is x squared plus 6x plus 8. Now look at that. We just proved that this standard form is equal to that factored form, right? Multiplying it out. Again, if you want to use the box method, awesome. If you want to distribute that and just kind of keep track of what you're multiplying, however you remember multiplying these is totally fine. What I want you to do, and I'm going to give you several minutes to work through these. There's 3 more on this paper that I want you to multiply out. Prove to me that the factored form is equal to how it's written there in standard form. Okay, now my challenge for you is when you get to what I'm going to call number 3, it has no number, but this one right here, it looks different. Did anyone notice what's different about that one? Ezzy, what do you notice?
There's 3 times 2.
Yeah, it's 3 times a 2. How do I multiply that? If I'm using the box method, what am I going to need to do? Ellie? Yeah, absolutely. You're just going to kind of make that box bigger, right? Remember that this will be one side of your box. It'll have 3 spots at it. And this will be the other side of your box, right? Multiply them out. Prove that what it says in factored form is equal to that standard form. But try them and then check with people around you. Okay, I put two more kind of written that I wrote down here. I know a lot of you made up some really good ones that you swapped. Some of you are still multiplying out your messy ones that you swapped. But here's a couple that I want you to just think about. You can write them down and try them, but I want you to think about what would we do, right? We started off with these easier kind of set up 2x2s we're really familiar with. You know how to multiply those. What happens as it gets bigger, right? It's a lot of the same kind of principles, but what happened as our boxes, as our kind of multiplication changed? When it wasn't a 2x2, what happened to our box, or what happened to our multiplication? Just kind of had more steps, right? It got bigger. What happens if you look at these 2 problems? This first one, how would I multiply these 2 things together? What's the same, or what's different from the other ones you just did? Yeah, we would make a square of a 4x2, right? Or distribute, just make sure everything is distributed into everything else, right? So this one, maybe we would have a box that just looked bigger, but would have the same kind of setup, an x and a 2, x cubed, 2x squared, x minus 5, the same mechanics that you just did. What about this problem here? What would happen if I was multiplying more than 2 of them together? We can't really make our box, this doesn't really make our box bigger, right? Because we can't have 3 sides to a box. It's not a box anymore. That's not how it works. Any idea how we might multiply something like this? Allie, what do you think?
I don't know if this would work, but can you do just the first 2 parentheses and then afterwards?
Yeah, absolutely. Multiply these 2 together,
Yeah.
right? And you would end up with x squared plus 5x plus 6, and then multiply it by the next part, right? Kind of do it by pieces. But what I want you to kind of think about is the mechanics of using that box or distributing works no matter what the size is, right? When we dealt with quadratics, factored form was always a 2 by a 2. That's what made it quadratic. In a polynomial, how big could the pieces be that we're multiplying? They could be any size, right? We could have a 10-term expression multiplied by a 10-term. Technically, you could make a box for that, right? The mechanics are the same, even though it starts to look a little bit different. But we would multiply the first 2 together and then multiply it by the last one. If you had more, you would just kind of keep going with that, right? Okay, our last thing, and then I'm going to give you some time to work on some homework today. You see 2 equations here. In a moment, we will graph these. But at first glance, what do you notice is the same or different between these two equations? This is your last page in your notes. What's the same? What's either the same or different between these two? Ezzy, what do you notice? Okay, this. Yeah, that fraction out in front, absolutely. Everything else besides that is the same, right? What will the zeros be on these two equations? Exactly the same, right? Remember we looked at how to find those x-intercepts a couple classes ago? What will happen if we graph these two? Any idea what they're going to look like? Are they going to be the same graph? What's going to be different about them, do you think? One's what? When you say half, what do you mean?
Like if the y value for the first is 7, it'll be like 2.5.
Yeah, it's kind of like that stretch or shrink that we looked at with quadratics. That one with a half is going to be kind of squished together, right? It goes through the same x-intercepts. It has the same shape. It goes in the same direction, but it's kind of squeezed together. What I would encourage you to do is I want you to get out either your Chromebook, or if you have a graphing calculator in front of you, type these two in, see what they look like. What's different about them? How are they the same? Right? This asks right here, describe how the two graphs are the same and how they are different.
The second graph is
What do you mean?
like a half.
Just squished, right? You should see the exact same shape. So for example, if this isn't the same graph, but if it looked like this, maybe your second graph would kind of, right? It would be squished down. I know I hear you saying half of it, but I want you to kind of think about how all those kind of change this way, right?
Are we gonna have to graph them?
I don't remember. I think so, but not in this idea. This, we're just kind of starting to look at how it's changing. I know we go into some graphing things in a couple of lessons, but it's not quite the same one. Okay, so this is what you should see. If you haven't graphed it yet, I would encourage you to keep kind of going in to do that. What we're going to do, that's where we're going to call it a day. I'm going to, in a moment, come and give you your ticket outs for you to do, kind of a check-in on where you are. When you finish with this and get it to me, I would encourage you're going to have probably when you're done with this, about 15 minutes left. I would encourage you to go in and at least open the homework, get started on a couple of them, because while it's fresh in your brain, remember this is your own knowledge. Please don't talk to other people as you are doing this.